Hello everyone, welcome to the channel of Algocamp. So now on this particular channel, we are actually releasing a series on data structures and algorithms where we are going to talk about some of the most important data structures and algorithmic topics which are extremely important for your upcoming software engineering interviews. Apart from that, these are some of the I would say topics that are very helpful in your day-to-day engineering job as well. We have already released a couple of series around searching, right? And we got a really good response on that. And from here, we are going to put really some awesome content around DSA. In most of these lectures, we will try to ensure that we focus on the intuition building aspect of the things, that how you are able to think about something, what are some of the things that people actually neglect but are going to clear some of the really important fundamentals. We are going to see coding implementation, but trust me, my focus is not going to be on the language delivery aspect of the things, that okay, you have to code this in C++ or Java. A lot of problems we have coded in multiple languages. Maybe some of the problems will be in C++, some will be only in JavaScript. I believe if you are somebody who is preparing for an interview, language in 2025 should not be a constraint, because most of the people can actually use ChatGPT to do language conversions. So my motive here is to make sure that you understand the concept in depth. You actually see how exactly somebody might have thought about the problem when they were carving out the problem, what can be some initial thought process, how you can actually drive yourself towards the solution. I believe these are going to be some really important videos that will be really helpful for your upcoming career. So do let us know what is your feedback. We are going to release a lot of more topics. Do let us know what all topics you want to have first, right? And the feedback is going to be important. Also, in case you are actually thinking to level up, you want to learn things with respect to low-level design, high-level design, overall system design for interviews, or you are somebody who wants to do project development in Spring Boot, you want to learn advanced Spring Boot concepts, or let's say advanced Node.js concepts, then we have a lot of courses, live courses running on algocamp.io. So you can check out the website courses.algocamp.io/learn, and there are a lot of courses that are actually listed. A lot of great discounts are actually going on all the courses as well. Do check them out. For each and every single course, we are going to add you to a dedicated Discord community where you can get your doubts resolved as well. All of the courses, we have made sure that we talk about things from the very beginner to the very advanced level that is going to help you level up in your career as a software engineer. So that being said, let's start the video without any further delay. So now we are going to talk about a new sorting algorithm called as Mergesort. Right. Now, Mergesort, I believe a lot of people learn in college days, right? Whenever they prepare for interviews, Mergesort is one of the algorithms that like most of the people have to learn, right? It's very efficient, it's very important, but I believe not a lot of people understand it with the best of their ability. We are going to decipher small components of Mergesort in a very elegant way, and then we will try to exactly see that why Mergesort is done this way only, why not some other way. So first of all, let's try to get into a situation. Okay, let's try to get into a situation. So now we have already solved a problem where, let's say, if you have two sorted arrays, if let's say you have two sorted arrays, 1, 7, 19, 20, 2, 3, 4, 18, 21, 22, right? Both of them are sorted in increasing order. Can I say that? If we have been given two sorted arrays, then we can very easily merge them. We know the algorithm of how to merge two sorted arrays, right? How to merge two sorted arrays. Now, based on this algorithm, if we would be able to do something, then that is going to be extremely helpful. So what Mergesort says that, let's say you have an array. Let's say you have an array which is initially unsorted. Let's say this array is unsorted. So let's say 9, 1, 6, -1, 3, 18, 2, 14. Okay. Let's say this is the given array. So before we start this particular video, I wanted to actually talk about a very small thing. So this video is going to actually help you understand a real system design interview scenario. We are going to try to mimic a 45 to 60 minute kind of like a round where we are going to solve a problem very similar to how you will solve a similar system design problem in this short time frame. Now, of course, when you work as a software engineer in a company, you have relatively larger amount of time and you can do a lot of more deep dives in even very small level features. But in an interview, the temperament is different, the approach is different, and a similar scenario is actually explained in this particular video. So do consume the content based on that. Also, if you want to see more deep dives and want to understand these topics in a much more deeper level concepts, then do check out the link in the description section below for our system design 2.0 cohort, where we have talked about a lot more concepts in a lot more detail, which will make you definitely a better software engineer. So let's just start the video. And initially this given array is unsorted. This given array is unsorted. Now, if this given array is unsorted, then what Mergesort says that, how about we write a function f, right? This function f, let's say, applies Mergesort and arrange the elements in increasing order, right? And arrange the elements in increasing order from, let's say, some range I to j. That is, from the index I to j, what does it do? This function applies the algorithm Mergesort. We don't know about the algorithm of Mergesort for the time being, but let's say this algorithm helps us to do sorting. So in the range I to j, this function can actually apply Mergesort and arrange all the elements in increasing order. So what we say is that, how about if you index this array 0, 1, 2, 3, 4, 5, 6, 7. How about if I apply Mergesort on half of the array, and then I apply Mergesort on the remaining half of the array. What did I say? This function f actually applies Mergesort. So let's say we will pass this region in the function f, and then we will pass this function in the region f. What the function f will do? It will arrange this particular region in increasing order and this particular region again in increasing order. Can I say that? So let's say you will get two regions altogether arranged in ascending order. So let me write it. This is -1, 1, 6, 9, and here we have 2, 3, 14, 18. Now technically these two regions can be represented or can be considered as two sorted arrays, right? This region can be considered as one sorted array. This region can be considered as another sorted array. And then what we can do is, in order to get this whole array sorted, we can merge them. So we have one sorted array, we have another sorted array. We merge the two sorted arrays, and finally we get a completely sorted array. How about if we do something like this? This is the algorithm of Mergesort. So what Mergesort says that, let's say we have to implement this function f that goes from the region I to j and helps us to sort the array from the region I to j, right? It helps us to sort the region from I to j. And how do we do it? We assume that, let's say, Mergesort will sort half of the array. The Mergesort function will sort half of the array. That means we are going to assume that f of arr, I, mid, this function works correctly. We are going to assume this. We are going to make an assumption out of this. We are going to make a recursive assumption out of this, that this half of the array, that is I to mid, let's say this is the mid, right? Let's say this is the mid. So I to mid will be sorted because this function will correctly work for I to mid. We are going to assume that. Then we are going to make one more assumption, that this function also works for mid plus 1 to j. That is, from this index to the jth index, it will sort the remaining array. Once these two regions are sorted, what we are going to do? We are going to merge the two regions and actually get a final sorted array. This is the simple algorithm of Mergesort, that it divides the array into two equal halves. It recursively sorts one half Then it recursively sorts the second half. Once both the halves are sorted, then it merges them. Now you might be thinking that, okay, but how it's actually happening? Let's think about it. So if I just cut this region out, okay, so 0, 1, 2, 3, 4, 5, 6, 7, right? Okay. First of all, we will divide the array into two halves. We will assume that merge sort will sort this half. Merge sort will also sort this half. What is this half? 9, 1, 6, minus 1, 3, 18, 2, 14. We are going to assume that merge sort will recursively sort this left half. Then merge sort will recursively sort this right half. We are going to assume that, right? We are going to assume that. In that case, we know that recursion actually doesn't do any magic, but it just consider the bigger problem in terms of the smaller problem. Then it again breaks down the smaller problem into sub-problems. So that being said, this array will again be divided into two equal halves, and this array will also be divided into two equal halves. So this half will become 9, 1. This half will become 6 minus 1. This will become 3, 18. This will become 2, 11. So you can see, you will first sort this half, then you sort this half, and then you merge it so that you can get this whole 4 elements as sorted elements. And that's not it. We will again break it down into smaller subproblems. Where this array of length 2, we will get 9 here, 1 here, 6 here, minus 1 here, 3 here, 18 here, 2 here, 11 here, right? So just think about it. Just think about it. You had this array, you divided into two parts, you recursively assumed that this left part will be sorted, this right part will be sorted. In order to sort the left part, you recursively again go deep and you assume that you will sort this left half and you sort this right half, and then you will merge to get this part sorted. Then you again divide it into two equal parts. You assume that we will sort this half, we will sort this half, and then we will merge them to get this half sorted. And just think about it. Once the array is of length 1, see now the region that you wanted to sort, we are talking in terms of region. So now the region that you wanted to sort is of length 1. If the region is of length 1, I can say that it is already sorted. Now we can start the step of merging. This array is sorted, this array is sorted. How do you sort? How do you merge two sorted arrays? We already know the algorithm. That means this will give us 1, 9. Then this is sorted, this is sorted. We will merge them. It will give us minus 1, 6. Then this is sorted, this is sorted. This is going to give us 3, 18. This is sorted, this is sorted. This is going to give us 2, 11. Now, this is a sorted array, this is a sorted array. We are going to merge them. What do we get? We get minus 1, 1, 6, 9. See, now this part is actually sorted and we merge them here also. We get 2, 3, 11, 18. And at last, this array is also sorted. This array is also sorted. We are going to merge them. It will become minus 1, 1, 2, 3, 6, 9, 11, 18. And you can see this is the sorted version of our given input array. Can I say that? Right. So that's how merge sort works. We will only see this much part. Like we will only implement this much part, that you have a whole array. You divide it into two parts. You recursively assume that merge sort will sort this half. You recursively assume merge sort will sort this half. And then you actually merge it. But inside, all of these steps are going on. Although I have shown the steps below it so that you can get a better visualization. But technically what will happen? When 9 and 1 will be hit, you will go back because you will return. This is the base case. The single length array is going to be the base case. You are going to merge two single length arrays and the changes will be done here only. So we will see it with respect to like what level based changes you are actually doing. But this is the recursion tree that you can imagine with respect to merge sort, right? This algorithm is so powerful, and we will also see what is the time complexity of this algorithm. But this algorithm is so powerful that it surpasses the efficiency. In terms of efficiency, it surpasses other algorithms like insertion sort, bubble sort, and there are few other algorithms also that we are going to learn. It is sometimes for some cases even better than that. So the overall logic is this function f can sort the array from the range I to j. How to implement this function? We don't know. We will recursively implement it. So we will assume that you will sort the first half of the array correctly. We will assume this. Then you will sort the second half of the arrays correctly. In order to sort the whole array, you will just merge the two halves. This is going to be our recurrence relation. And based on this, we are going to do the coding implementation and implement merge sort. Now let's start implementing merge sort. So what we are going to do, we are going to say void merge sort, and we are going to pass a vector of int here. Let's include vector. Okay. Now what we are going to do, we are going to write a function std vector of int f, which takes an array, right? That is, it takes a vector of integer arr. It takes a value I, that is the starting range. It takes a value j, that is the ending range. And this actually applies merge sort in the range I to j. And it returns a sorted array, right? This returns a sorted array. Okay. So we are going to apply merge sort using this algorithm, and it will help us to actually return a final sorted array. Now let's start implementing our function f. So inside our function f, what we are expected to do, we'll calculate mid. Okay. So we can say I plus j by 2. This is going to be our mid. And now what we are going to say is that we are going to say just go and sort your left half and give me a sorted array which I will call as left. I to mid. That is, from I to mid, sort the whole array and return me a new sorted array that is called as left. Then similarly, f of arr comma mid plus 1 to j, that is, go and sort the right half and give me a sorted array right. Give me a sorted array right. What is my operation going to be? I'm going to merge the two sorted arrays. Now merging two sorted arrays we have already implemented here. I'll just copy this, paste it here. Right. So this algorithm we have already implemented for merging two sorted arrays. Right. What we can do, we will say std vector of int result is equals to merge two sorted arrays. We'll pass the left array which is sorted, we'll pass the right array which is sorted, and at last we'll return result. Okay. And here we will say arr is equals to f of arr comma 0 comma arr dot size minus 1. Right. That is, whatever is your array, starting from the 0th index till the last index, we are going to apply merge sort. Right. Base case. Base case. The base case will be if I becomes equals to j, that means this is a single length array. Right. For a single length array, you are going to return a new array. So we can say return a new vector of int which will be having a single element arr at I. Okay. So we are going to return a vector which will be having a single element arr at I. So what will happen if, let's say, you have a single length array, it will return the single length array. So two single length arrays will be returned on left and right. This is a single length array, this is a single length array. When you will pass on into merge to sorted arrays, the single length array and the single length array will be combined to form a two length array, which is here. And then you're going to return that. And slowly and steadily, all the arrays are going to be built. So if we have a vector, ARR, and we apply merge sort on ARR, right? And because we have passed everything by reference, setting ARR is equals to this is going to set the new array inside ARR. Let's apply a for loop. Right, and we are going to print ARR at I. That's it. So let's try to run the code. Merge sort minus o run, and we'll pass a flag for std is equals to c++ 14. If you run it, you can see everything compiled, and we have the final array as a sorted array 1 2 3 4 5 6. If you take a odd length array, let's say an odd length array, let's compile again, run again, and you can see we have the final answer. So this is going to be the overall output when you apply merge sort on a given array which is expected to be sorted. Okay, so let's try to dry run the implementation of merge sort that we have written. Okay, now if you carefully see in the call stack, let's say we will pass an array and call the function merge sort here. Merge sort with the given array. Let's say the array is, original given array is 5 4 3 2. Okay, I'm taking a very small array. On line number 14, you actually call the function f. You call f with arr, comma 0, comma arr dot size minus 1, that is 3. Size of the array is 4, 4 minus 1 is 3. Okay, you will check. So here the value of I is 0, j is 3. Is I and j equal to each other? No. So this is not the base case. You will calculate the mid. Mid becomes 3 plus 0 by 2, 1. So you will say, go and sort my left half of the array. That is, go and make a call to f of arr, comma 0, comma 1, right? And we are going to leave this function call on line number 7. Okay, on this line we actually left the function call and we moved here. This is a new function call. I is equals to 0, j is equals to 1. Okay, is I and j equal to each other? No. So we'll calculate mid. Mid becomes 0, 1 plus 0 by 2 is 0. And you again make a function call f of arr, comma I, comma mid. So again we leave this on line number 7 and we make a function call to f of arr, comma 0, comma 0. Now here I is 0, j is 0. So this is the base case. In the base case, what do? You return a new array, arr at I. So from here, you are going to return an array, arr at I. What is I? 0. So you're going to return a new single array, 5. Okay. And you come back. So we left this function call on line number 7. On line number 7, we initialize a variable left, which is storing the result of the function call. The result of the function call is 5. So 5 is actually stored inside left. 5 is actually stored inside left. Now line number 7 is done. The next line to be executed is line number 8. In line number 8, you again make a function call f of arr, comma mid plus 1. Mid is 0, so 0 plus 1 is 1, comma j. Now here you can see again I and j are equal to each other. You will again return a new single vector with arr at 1. Arr at 1 is 4. and that's it. You return this. And now you're back on line number 8. On line number 8, whatever was the result of the function call, you store it inside a variable right. So here, this will be stored in the variable right. Now, you have a left array which is sorted, you have a right array which is sorted. You call merge two sorted arrays, left comma right, and store the result inside result. So here, you'll be having now a variable result, which will be having 4 comma 5. Which will be having 4 comma 5. And that's it. You're going to return this result to the previous call. So 4 comma 5 is returned to the previous call, and that's it. So in the previous call, you left it on line number 7. On line number 7, you said that whatever is the result of the function call, you store it in left. So here, left becomes 4 comma 5. So that means this was our call, right? That you go and sort the left half. So you got the sorted left half in a new array. Now the next line to be executed is line number 8. F of, now you make a call to mid plus 1 comma j. Mid is 1. 1 plus 1 is 2 comma 3. F of 2 comma 3, right? You check, is I or j equal to each other? No. You calculate mid. Mid is 3 plus 2 by 2. 5 by 2 is 2. You make a call from f of 2 comma 2. F of ARR comma 2 comma 2. Right? And you leave this on line number 7. Now here, I and j are equal to each other. So you return a vector. That is left is equals to ARR of 2. What is ARR of 2? 3. So inside left, you just have a 3. And that's it. Now you are back on this function call where you got 3 inside the left variable. You left it on line number 7. You will move to the next line, that is line number 8. In line number 8, you again make a function call to mid plus 1 comma j. Mid plus 1 is 3, j is 3. So you make a call to f of ARR comma 3 comma 3. This is again base case. You will return a new vector of ARR at I. What is I? 3. So ARR at 3 is 2. So you will return right is equals to 2. And now you are back here. You have your left and the right. In line number 9, you say merge two sorted arrays. So 3 and 2 you are going to merge, and you are going to form a result is equals to 2 comma 3. And then you will return this result. So when this result is returned, what will happen? You will come back here on line number 8, and here you have access to the right array, which is 2 comma 3. Now in this function call, you have your left array, which is sorted. You have right array, which is sorted. You merge the two sorted arrays. When you merge the two sorted arrays, your result becomes 2, 3, 4, 5, and you return the result. That's it. You come back to merge sort, this function. Whatever is the result of this function call, you assign that result inside ARR. So now ARR is actually pointing to a new array, which is having 2, 3, 4, 5, and that's it. This is how you will be sorting your array using merge sort. So now we are going to implement merge sort. In order to implement merge sort, I'll first implement the merge function. This merge function actually takes an array. It takes left I, left j. What is left I, left j? It is the left sorted region that we are going to merge. Then we are going to take right I, right j. What is this? This is the right sorted region, and we are going to merge this whole region. Okay, cool. How we are going to merge it? First of all, I'm going to extract out all the elements in the region left I to left j inside a new array. So let's say I will create a new array. Let A is equals to new array, and I can just write array, and the size is going to be left j minus left I plus 1, and there will be another array B with the size right j minus right I plus 1. Okay, and then I'm going to copy all of the elements from this region inside A and from the right region inside B. Okay, let's do the quick copy. So for let I is equals to left I less than or equal to left j, I plus plus, we will say let's keep something like let k is equals to 0. We'll keep an index k and we will say a of k is equals to arr of I, and we will do k plus plus. Okay, then we will reinitialize k to 0 and we will do the same thing for the array B. For the array B, but this time the bounds are going to be from right I to right j. Okay, so here what I'm doing, I'm copying, let's say if I got this sorted region, let's say if I have an array, right, 1 2 -1 3. Okay, this is a sorted region, this is a sorted region. I have to merge them. So what I'm doing is I'm creating a copy of this sorted region inside a new array A. I'm creating a copy of this sorted region inside a new array B. I will merge them inside a new array C and then copy back all of the elements of C inside the original array, right? So that's what I'm doing. So now let's start. So now I have a sorted array A, I have a sorted array B. Now we want to push this inside a array C. Okay, so we will say let I equals to 0, j equals to 0. Okay, we'll say while I is less than a dot length and j is less than b dot length, we will say if a of I is less than b of j, I will do c dot push a of I. Otherwise, I will do c dot push a of j, right? Okay. Now, if this while loop has ended, then maybe one of the array got exhausted. So we will check. If A got exhausted, then we will be still having some elements left inside B. So this should be B of j, right? I will do this, right? And if I'm having B array exhausted, then I'll be having some elements left. I'll be having some elements left inside the array A. So we'll say C dot push A of I, right? One more thing that we need to do, once we have pushed the ith element, I need to do I plus plus. If we have pushed the jth element from the bth array, then we need to do j plus plus, because I is the pointer that is going to point to A, j is the pointer that is going to point to B. Again, I plus, here we have j plus plus and here we'll be having I plus plus. So now in the array C, we have the whole sorted region of A and B merged. Now what we are going to do, we are going to copy back C to ARR. How we'll do copy back? We will say, again, let's say k is equals to 0, right? We will say for let I is equals to left I less than or equal to right j, I plus plus, and we will say ARR of I is equals to C of k, and then we do k plus plus. So this k index is going to iterate on the C array, and then this region is going to be coming inside ARR, and that's it. This is going to merge everything for us, right? Now I'm going to write a function f. You can replace the name f with Mergesort. It is going to take an array ARR. It is going to take a region I. It is going to take a index j, and from I to j it applies Mergesort. In order to apply Mergesort from I to j, we need to first of all get the mid. So we'll say let mid is equals to math.floor of I plus j by 2. And then we can say that just go and apply Mergesort on the left half, that is I to mid. Just go and apply Mergesort on the right half, that is mid plus 1 to j. And then what we are going to do, we are going to merge the array. The left region is I to mid, the right region is mid plus 1 to j, right? What will be the base case? What will be the base case? If I becomes greater than j, then we are going to return, because then we are having no length at all. And if I becomes equal to j, then also we should return, because then technically it's a single length array. So I can just merge both of the conditions here, that if I is greater than or equal to j, then we are going to return. This algorithm looks fine to me. Let's try to run it and see if it works or not. So let's get some elements. 9, 1, 6, -1, 3, 18, 2, 14. We'll apply merge sort to ARR. Right, and the whole region is going to be from 0 to ARR dot length -1. Okay, and then we are going to do console.log ARR. Cool. Let's see if it works. If there is an error, we'll try to debug. If you run it, you can see the whole array looks sorted to me. Let's add one more element to make it odd. Let's say -2. Let's say we'll add. If you run it again, you can see still the array is sorted. Okay, let's try with a few test cases where the array is already sorted. See, it still goes fine. If let's say we just have a 2 length array, it still goes fine. If let's say we just have a 1 length array, it still goes fine. So most of the test cases are working fine, and that is a simple implementation of merge sort. How we did it? I just said merge sort my left half, merge sort my right half. Then I'm going to merge my left half to the right half. In order to merge the left half to the right half, first of all, you will extract left half in an array A. You will extract right half in an array B. Then you will merge A and B into an array C, and then copy back the elements of C in the region from left I to right j. That is the coding. That is going to be a simple coding implementation for merge sort. So in order to implement merge sort, instead of like just creating the arrays inside the merge function, right? Currently, if you see the merge function, I am passing the regions, that this is the left sorted region and this is the right sorted region. Instead of passing the sorted regions, I can maybe pass the array, like this array A that I'm constructing inside merge function. I can maybe pass this array. This can also be done. So let's see. If I write a function merge where I have a left array and a right array, right? We have a function merge where we get a left array and a right array, and we have to merge these two sorted arrays. So here left is an array and right is an array, right? Both of them are arrays, both of them are sorted arrays, and we have to merge them. And finally, we will return another sorted array. So we'll say let result is equals to an empty array. We'll say let I equals to 0, j equals to 0. I is going to iterate on left, j is going to iterate on right. We will say while I is less than left dot length and j is less than right dot length. We will say if left of I is less than right of j, we will do result dot push left of I, and I'll do I plus plus. That is, if the ith element of the left array is lesser than the jth element of the right array, that means this ith element should be given preference, and we need to add it first in the result. Otherwise, we need to add the jth element of the right array, and we'll do j plus plus. Then maybe one of the array can get exhausted. So let's say if right array got exhausted, then this loop will still go on, and we'll say result dot push left of I, and I do I plus plus. And maybe the first array goes off first, and we have still elements in the right array. So we'll say j less than right dot length. This loop will still go on. J plus plus. At last, in the result array, you have your final sorted arrays. So inside the merge function, in the result array, you have your final sorted arrays. That is, the left sorted array and the right sorted array is merged into one sorted array inside result, we are going to use it. So now maybe I can write a function, let's say f, that is going to actually do merge sort for us, right? It's going to take the original array. It is going to take a region I and j, right? First of all, if I becomes equals to j, then we can say that it is of only single length, right? If I and j becomes equals to each other, that means you're pointing to the same element. That means you have a single element that you have to merge. If you have a single element, then what you do? You create a new array, temp, and inside temp, you store ARR at I. Inside temp, you store ARR at I. So see, temp is an array in which you store ARR at I and you return temp. That means you are now, instead of constructing new arrays inside merge, the moment you hit the base case, from there only you created a new array. See, I created a new array here only. And then I will say, let left is equals to f of ARR comma I comma mid. Let's calculate mid. Let mid is equals to math dot floor of I plus j by 2, right? And let right is equals to f of ARR comma mid plus 1 to j, right? So see what's going on. Now this function f returns a new array. Previously, our function merge sort was not returning anything. It was like making changes in the same array. So we didn't need to bother about the return value because see, we were like returning nothing. Here we are actually returning an array. That means every function call is going to receive an array. So when you sort your left half, you will get a left sorted array. When you sort your right half, you will get a right sorted array. And then you can say, let result is equals to, we will call merge on the left sorted array and the right sorted array, and we will return result, right? We'll write another function merge sort, which is going to take an array, and internally this function merge sort calls f with ARR comma 0 comma ARR dot length minus 1, right? This kind of segregation you can also do here, because when on the call site only I'm passing the indexes, right? Here the call site will look more clean. Let's say let ARR is equals to 916 minus 1 318 214. I will just call merge sort with array ARR. So when you call merge sort, it calls the function f with 0 index as I and last index as j. So you don't need to bother about that. You can just directly pass the array. And then let's see what is this. Now, merge sort function will return an array because this function f returns an array. So a new array will be returned to you. So you will store the result of the new array inside ARR. Now let's run it. And you can see the array still gets sorted. So in both of the cases, you are going to create new arrays. Here you are creating new array here and this new array here. In merge sort, the previous implementation, in the merge function, every time we were creating new arrays. So space is going to be taken. And if you just carefully see, we are using new arrays or new data structures to actually manipulate the elements. So merge sort is not in place, right? We'll talk about this also. So extra space is getting used, but we'll talk about the space and time complexity and the in place property and everything in some time. But the overall coding implementation is not much different. Either you consider space inside the function which is recursive, or you consider the space inside the merge function. Both of the implementation are equally efficient in terms of time and space. What is the time and space? We will talk about it. So let's start talking about the fact that whether merge sort is in place or not. We'll talk about space and time complexity later. But if you carefully see that we have implemented merge sort in a recursive fashion. So we can see that merge sort is a recursive algorithm, right? Merge sort is a recursive algorithm. If merge sort is a recursive algorithm, that means some amount of extra space is going to come up from call stack. There will be call stack that is going to be used. I'm not doing space analysis for the timing. I'm talking about whether it is in place or not. So extra space is getting used from call stack. But apart from call stack also we are using extra space. Apart from call stack, if you see, whenever we actually create new arrays, in these arrays, we actually push our elements, then we do the manipulation inside these new arrays and then bring them back in the original array. Or even if you see the other implementation, then we are even leaving the original array altogether and we are like storing altogether a new array only. That means we are manipulating data in external data structures, and hence merge sort is not in place. That's going to be the most important observation that you can directly make without actually doing the space and time complexity analysis, that merge sort is definitely not an in place algorithm. It's going to take extra space, and like in that extra space, it is going to also manipulate the data. It could have been that it just takes the call stack space but keeps the element within itself. Then it would have been really easy. But it takes the extra space, but it doesn't keep the elements to itself, right? Although you might get a feeling, that if we can somehow modify merge sort, such that instead of creating two different arrays, if we can in the same array do the merging, is that possible? So technically that is going to be a very hard thing to do, right? Because if you will just immediately change the elements in the original array only without storing it outside, you will lose the track of elements. So eventually you have to make these new arrays, right? There is something called as in place merge sort also that hampers the time complexity. First we'll learn the time complexity, then I'll come to in place merge sort. That hampers the time complexity, but it definitely optimizes over space. We will talk about in the upcoming parts, but for the timing, the most important observation that you can make is the default implementation of merge sort is not in place.